Here we want to evaluate the electric potential around a point charge. There's a formula for doing this, and it is V equals KQ over R. Notice that the R is not squared in the potential formula. This is actually similar to the potential around a point mass formula from gravitation. The formula would be Vg equals negative G m over R. But this is, of course, the electric potential that we're talking about now. So this is gravitational potential. And this is electric potential. All right, so similar to gravitational potential, a point charge cannot exert a potential at its own position. It would be undefined there because the radius r would be 0. And also we find that when r is infinity, the electric potential around the point charge is 0. So way out here, let's say at point C, which is at an r of approximately infinity, we would find that the electric potential there would be 0. And the potential is going to only increase as we get closer and closer to a positive charge. Now this is a little bit different from the potential around a point mass. Point mass would create a potential well where the values get more and more negative as we move toward the mass. When it comes to a point mass in space, what we found in Physics 1 was that a point mass will create a potential well where the potential gets more and more negative as we move in toward the point mass. We said that the potential would be 0 at an r of infinity for a point mass. And you can see that due to the formula for potential, it's got a negative in it. We're going to always get negative values for gravitational potential. And so if you're standing out here toward infinity, your V is approximately 0. But as you move in, it would be, let's say, negative 1 joule per kilogram. And then negative 2 joules per kilogram. The idea being that if you're located out here, masses have more potential energy out there than they would closer. So if we have a point mass that's located in space, a mass at point A will actually have more gravitational potential energy than B would. So the idea is that mass A can be accelerated a great distance, whereas B is closer, so it doesn't have as much potential to be accelerated. The work that would be done here is not as much. Now let's look at the concept of potential around point charges. Now, if we have just a positive charge in space, what we'll find is that our potentials around a positive charge will actually be positive values. Okay, and so instead of getting a well, we'll actually get a mountain. According to the formula, V equals KQ over R. There's no negative in this formula, and if our Q is positive, then our voltage values will be positive. Now we still have the condition that out at infinity, we will have a voltage of 0. But as we get closer to our charge, we'll go up in potential. All right, what does this mean in a two-dimensional situation? Well, a positive charge at point B has more ability to be accelerated by the field than a positive charge at A. See, A can be pushed out by this charge all the way to infinity. And B can be pushed out there too. But as we see, B can be pushed farther than A can. So, with this in mind, we find that at point B, we have more electric potential energy. And at A, we actually have less electric potential energy. Now, what's the voltage like around a negative charge? Like a mass, a negative charge will actually create a well. According to the formula, V equals KQ over R, where if Q is negative, then the voltage will be negative as well. Out at infinity, we still have that the voltage is 0, but as we get closer to the negative charge, we will form negative values. All right. If we were to, say, put a positive charge in the field near our negative Q, and let's just compare A and B when it comes to potential energy. So A has a lot of ability to be accelerated through space until it reaches the negative charge here. B doesn't have as much ability to do that. So at A, we have more electric potential energy than we do at B. And that is the significance of the negative values. We have more electric potential energy out here than we do closer to the charge. All right, now that we have that understanding, let's just do an example problem here. What is the electric potential at a point infinitely far away from charge Q? That would be the potential at C, and I had already answered that one. The electric potential at point C will be 9e to the 9 Newton meters squared per Coulomb squared times the charge of Q, which is 1 Coulomb. And then we'll divide by the radius of infinity. But if you divide a finite number by infinity, you're going to get 0. Now let's find the electric potential at point B, which is a distance of 4 meters from charge Q. All right, that's going to be 9e to the 9, 1 Coulomb, 4 meters. It's 2.25 times 10 to the 9 volts. Now let's find the electric potential at point A. That would be this point here. Will it be a larger value or a smaller value? Well, this is a positive charge, so these potential values are going to be positive, and they're going to get bigger and bigger as we get closer to the charge. So let's find out. I'm getting 4.5 times 10 to the 9 volts, so it is a greater potential at A than B. So anywhere on this equipotential circle here, the potential will be 4.5 times 10 to the 9 joules per coulomb, which is a volt. And anywhere on this equipotential for B, we'll find that the potential is 2.25 times 10 to the 9 joules per coulomb. All right, so basically doubling the distance from the charge cuts the potential in half. All right, so this problem says, what is the change in potential energy if a proton moves from infinity to point A? Okay, so we're talking about taking a proton here at C and then just moving it to point A. The path that it takes actually doesn't matter. This type of thing is path independent. Okay, one thing we can use for this is the formula delta U equals Q delta V. All right, so let's plug in the charge of the proton. And now we need the potential difference between C and A. So I'm going to do the potential at A minus the potential at C. All right, so that's going to be this. We see that our potential at A is much higher than the potential at C, so it's going to be 4.5 times 10 to the 9 minus 0. I'm getting 7.2 times 10 to the minus 10 joules. So the meaning of this is that's how much work it would take to physically push the proton from infinity to the location of A. It's difficult to move it from infinity to A because the positive charge doesn't want to be near this positive charge. It would require energy to move it in that close. And the work that you did would be transformed into what's called electric potential energy. Let's find the change in potential energy if a proton moves from point A to point B. Well, I'm just going to use the same formula for this. Only this time we'll do VB minus VA. That'll be our potential difference. So we'll have this. All right, that's the calculation we want to do here. Let's see, I get negative 3.6 times 10 to the minus 10 joules. And you always want to think about the signs in these types of problems and see if they make sense. We're talking about moving a proton from a high potential to a low potential, and it makes sense that proton would lose potential energy in moving closer to infinity, moving farther away from the other positive charge. Finally, what is the change in potential energy if the proton moves back from B to A? Well, using our previous calculations, that'll be easy to answer. We can take our answer from the previous question and we'll just switch the sign. If the proton loses 3.6 times 10 to the minus 10 joules moving from A to B, then it must gain 3.6 times 10 to the minus 10 joules in moving back. The calculation would be we would reverse VA and VB. Okay, and that would be and that would give us our answer.